We all know that the atom consists of a nucleus, where the mass of the atom is concentrated. Around the nucleus, there are the electrons, which are negatively charged. The electrons usually occupy what we call electronic shells or levels. Those levels, we give them the symbols K, L, M, and so on. To describe the electrons around the nucleus, we use the 4 quantum numbers. The first quantum number is the principal quantum number. So the principal quantum number that we give it the symbol N is the number of each shell. For example, N for K shell is equal to 1. N for L shell is equal to 2. And the N for the M shell is equal to 3. So this is a principal quantum number, is actually the number of the shells surrounding the nucleus. The angular or orbital quantum number, which we give the symbol L, is a quantum number that we use to know how many subshells we have. So each shell of those shells is actually divided into subshells, and the number of the subshells is what we call the angular or orbital quantum momentum number. The value of L is equal to 0 to n minus 1. This means if I have something like n equal to 2, the L value would be equal to 0, and n minus 1, we have here n is equal to 2. This means 0 and 1. For the orbital quantum number 0, we give it the symbol S, and for 1, we give it the symbol P. 2, we give it the symbol D, and the subshell where L is equal to 3, we give it the symbol F. So, like we said, we have the shells is subdivided into subshells, and those subshells are called S, P, D, and F. S here where L is equal to 0, P, L is equal to 1, D, L is equal to 2, and F where L is equal to 3. Now moving to the magnetic momentum quantum number, and this magnetic quantum number gives us the number of orbitals in each subshell. So each subshell consists of a smaller sections. We call them orbitals. Those orbitals where there is a probability of finding an electron around the nucleus. For example, if we looked at the S subshell, it has one single orbital, and this orbital can take up to 2 electrons, where B consists of 3 orbitals, and each one of them can take up to 2 electrons. This means the total number of electrons that can occupy P subshell is equal to 6 electrons. The magnetic momentum quantum number that we give it the ML symbol is equal to minus L 0 to L. Let's take an example similar to the previous example. We had N is equal to, so we have L is equal to 0 and 1. Now if we looked at the values of L for L equal to 0 and 1, this means we have here S and we have 1, which is P. The ML for L is equal to 0 is equal to 0. This means we have one single orbital. This is the one single orbital of the S subshell. Now for ML of L equal to 1 is equal to minus L, which is minus 1, and 0, and 1, which is L. So when the L equal to 1, we have ML is equal to minus 1, 0, and 1. So this is why we have 3 orbitals in P, because L equal to 1, which is the suborbital B, actually has ml values -1, 0, and 1. So this is why we have 3 orbitals in the p subshell. Now for the spin quantum number, we said each orbital, so each one of this segment, we call it orbital, so each orbital can take up to 2 electrons. To minimize the repulsion between the electrons, each electron is spin in opposite direction to the other one. So they are either rotating anticlockwise or clockwise. For the anticlockwise, the value of the S, the spin quantum number, it is equal to +12, and the spin quantum number for the value of the electron revolving clockwise is equal to -12. So the spin quantum number describes the direction of the rotation of each electron. Now let's try to solve this exercise. To apply what we learned, deduce the 4 quantum numbers for n shell. N shell, this means we said we have K shell, L, M, and N. For K shell, N is equal to 1. N for L is equal to 2, and N here is equal to 3, and N here is equal to 4. This means the principal quantum number for N shell is equal to 4. Now the subshell is actually the value from 0 to n to -1. This means I have L equal to n minus 1 equal to 4 minus 1 equal to 3. This means I have the values 0, 1, 2, and 3. So the subshell notations, if I try to write down the subshell notation, we write the principal quantum number first, then we write the corresponding subshell to each L number. And here I have L is equal to 0. This means I have the subshell S, and here subshell P. I'm using here the principal quantum number in each one of them in the subshell notation. Now the 2 L corresponds to D subshell, and the 3, this is the value of the L, corresponds to F subshell. The magnetic quantum number, we said it is equal to the values from -L, 0, and +L. For S, where I have L value equal to 0, this means I have the value of magnetic quantum number value is equal to 0. This means I have number of orbitals equal to 1. S always has one single orbital. Now for L equal 1, this means I have the magnetic quantum number values from -L, -1, 0, and 1. Now for L equal to 2, this means I have magnetic quantum number values -2, -1, 0, 1, and 2. Now for L equal to 3, this means I have the magnetic quantum number values -3, -2, -1, 0, 1, 2, and 3. If I try to count the number of orbitals here I have 1 orbital, here I have 1, 2, 3 orbitals, and here I have 1, 2, 3, 4, 5 orbitals, and here I have 1, 2, 3, 4, 5, 6, 7. So I have 7 orbitals. So the total number of orbitals is equal to 1 plus 3 plus 5 plus 7 equal to 16 orbitals. Those 16 orbitals can take up to number of 32 electrons because each orbital can take 2 electrons. This means I have to multiply the 16 by 2. This means the N shell can take up to 32 electrons. We can use also another way to know the number of electrons in N shell, and the rule states that the number of the electrons in N shell is equal to 2n squared. If we apply it to the value of n, I have the value of n is equal to 4. 4 squared multiplied by 2 equals to 32 electrons.